Bismillahirrahmanirrahim. Okay, ji. So we will continue our discussion on the topic heat transfer by extended surfaces. Remember, in previous class, what we discussed was the general solution for the fin and its different cases. सो फॉर एग्ज़ाम्पल केस वन के बारे में हम डिस्कशन कर चुके थे कि इट इज़ हैविंग वेरी लॉन्ग लेंथ एंड टेम्परेचर एट द टिप ऑफ द फिन इज़ इक्वल टू सराउंडिंग फ्लूइड टेम्परेचर. केस नंबर टू हमारे पास था कि द फिन इज़ ऑफ फाइनाइट लेंथ एंड it loses heat by convection from its tip. So केस नंबर वन और टू में क्या डिफरेंस है कि इन केस नंबर टू द लेंथ ऑफ फिन इज quite short as compared to case number 1. Now case number 3 is we can consider the tip of the fin is insulated such that there is no heat transfer rate from its tip. So let's discuss the cases one by one. So as you can see here, if I plot temperature profile for case number 1, how we can plot temperature profile? That we can plot by using the equations that we will develop in the coming slides. Okay, so as you can see, the tip of the fin for case number 1 is having the same temperature as ambient temperature. Case number 1 is the length of fin is quite large. It is having quite long length, so we can say the temperature in this region is approximately equal to surrounding fluid temperature. So it means that there is no heat transfer rate, there is no heat exchange between the fin at this region and outside fluid. So this is our case number 1. Let's discuss its equations. So we have already discussed, this is the boundary condition for our differential equation, and we have already introduced theta. Theta is basically temperature difference, temperature of fin minus ambient temperature. So boundary condition at this region, which is the region at which the extended surface is attached to base surface, this is at x is equal to 0, theta is equal to theta naught or theta b, and theta b is equal to tb minus t infinity or t naught minus t infinity. This is boundary condition number 1 for case number 1. Now boundary condition number 2 for this case is, we will apply boundary condition number 2 at the tip of the fin. So when x is equal to L and L tends to infinity, we can say that theta is equal to 0. Why theta is 0? Because temperature at the tip of the fin is equal to ambient temperature. So we can say theta is equal to 0 at x is equal to L, and L in this case tends to infinity. So putting these boundary conditions one by one in this equation A, what we try to obtain is value of C1 and C2 for case number 1. So after putting boundary condition number 1 in equation A, we get this equation 1, and after putting boundary condition number 2 in equation A, we get C1 is equal to 0 and C2 is equal to theta naught. Remember, during this video lecture, I am going to skip the mathematical steps involved in finding C1 and C2. By the way, these are given in slides. You can see it by yourself. that how C1 is 0 in this case and how C2 is theta naught. So after finding C1 and C2, we put it in equation A, which is our general solution. We obtain value of theta as this. Equation for theta is this, which means we have obtained temperature distribution for case number 1. So what this equation tells us, that for any value of x, we can have temperature of the fin for that region or for that value of x. Remember, this is exponential function. T naught is base surface temperature and T infinity is outside fluid temperature. Remember, we have already discussed m, and m in this case is under root hp divided by Ka. So now we want to find heat loss or heat exchange by the extended surface. So this we can find by using Fourier's law. Heat conducted to the extended surface at x is equal to 0, and obviously this heat is lost to the outside surroundings by convection. So if we put values in this equation or in this equation, we can have equation for heat loss by the fin. So in this slide you can see that heat conducted to the extended surface at x is equal to 0, and we have already equation for temperature, which is this equation. So if we find its derivative with respect to x and put x is equal to 0 and putting it in this Fourier's law, we obtain this equation, and this equation is heat exchange or heat loss by this extended surface for case number 1. So we have found equation for temperature distribution of case number 1 and equation for heat loss by the fin. Now coming to case number 2. Case number 2 is that fin is of finite length and the tip of the fin loses heat by convection. So let's discuss boundary condition for these. So in this case, the length is quite short as compared to case number 1, and the tip of the fin loses heat by convection. So a boundary condition number 1 remains same. Boundary condition is at the base of the fin. The base of the fin is the region at which the extended surface is attached to the base surface. So boundary condition number 1 remains the same. Boundary condition number 2 in this case is that heat conducted to the tip of the fin. Remember, tip of the fin is at distance L from the base surface. This heat is lost to the outside surroundings by convection. So this is our boundary condition number 2 for case number 2, that the heat conducted at x is equal to L is lost to the outside surroundings by convection. So again, we will use these two boundary conditions to find value of C1 and C2 for this particular case. And in this case, there are some lengthy steps involved to have the value of C1 and C2. For example, in this case, value of C1 is this equation, and value of C2 is this equation. So once we have found C1 and C2, we will put it in our general solution to obtain or to have equation for temperature distribution, and equation for temperature distribution in this case is this equation. Remember, I am not going into details that how we have derived these equations. Just you should know about the case and its boundary conditions. And after finding equation for temperature distribution, we can now find heat transfer from the fin, and this we can use again the same procedure, that heat conducted to the extended surface at x is equal to 0. What we have to do is we will find we will differentiate the equation for temperature distribution, and we will put x is equal to 0. We can have heat loss by the fin. So in this case, heat loss by the fin is this equation. Remember, we have introduced capital M, and capital M is equal to combination of these. So this is this is equation for temperature distribution for case number 2, and this is equation for heat loss by the entire fin for case number 2. Now discussing case number 3, again boundary condition for case number 3, boundary condition number 1 for case number 3 remains the same as we have discussed for the previous two cases. Boundary condition number 3 in this case is that the tip is adiabatic, so that there is no heat exchange between the tip of the fin and outside fluid. Remember, in this case, the tip of the fin is at different temperature from the outside fluid, but it will not exchange any heat with the outside fluid because it is insulated. So in other words, we can say that Q from the tip of the fin is 0. This is 0 because this temperature gradient at x is equal to L is 0. We can also write that dt by dx at x is equal to L is 0. This is second boundary condition for the third case, which is for adiabatic fin tip. Okay, so again we will repeat the same procedure. We will use these two boundary conditions to find C1 and C2, and after finding C1 and C2, we will put it in our general solution to have equation for temperature distribution, and then we will find heat loss by the fin. So after using boundary conditions, we get C1 and C2. So C1 in this case is this equation. We will put this C1 and C2 in our general solution, and we get equation for temperature distribution. Remember, this is cosine h, which is hyperbolic function. This is again hyperbolic function, and heat loss by the extended surface is heat conducted to the extended surface at x is equal to 0 after finding derivative of theta with respect to at x and putting x is equal to 0 and putting this in this Fourier's law, we can have equation for heat loss by the fin for case number 3. So this is equation for temperature distribution of fin for case number 3, and this is equation for heat loss by the fin for case number 3. Now this table represents or summarizes the three cases. The tip condition for three cases is given, the temperature distribution equation is given, and heat loss by the fin for the three cases is given. So if you have this table, you can easily discuss about the three cases of the fin. Now you can see in this table that the equations for case number 2 seems quite complicated. uh, we will try to simplify these equations for case number 2. So what we basically do is that we compare case number 3 and case number 2. Why we are comparing case number 2 and case number 3? Because the length is in both cases the length is finite. So now the question is, if we have two fins of equal dimensions and equal length, and one fin is insulated from its tip and the other fin is not insulated, and it exchanges heat to the outside fluid by convection. So we have this type of situation that we have two fins of equal length and equal dimensions. One fin is insulated from its tip and the other fin's tip is not insulated. So obviously this fin will exchange more heat with the surroundings because it is also exchanging heat from its tip. So now what if I increase the length of case number 2 by this much length, and remember this extra length exchanges heat with the surrounding such that its tip exchanges the same heat. But I have made one other change, that I have now insulated the tip of the fin. So what basically I have done is that I have increased the length of the fin as well as I have insulated its tip. So now basically we can say that these two fins approximately or nearly exchanges heat with the outside fluid equally, because this fin was exchanging heat from its tip as well, and in this case the tip is insulated but its length is increased. How much its length is increased? Its length is increased by half thickness if it is of rectangular profile, and if its length is increased by diameter by 4 if it is of cylindrical profile. So this new length is named as corrected length. So basically this is case number 2 and I am treating it as case number 3. So basically we can do is that we can use case number 3 relations for case number 2 by replacing L by LC. So instead of using these relations, we can use this relation for case number 2 and this relation for case number 2. We have simply replaced L by LC. So we have used relations of case number 3 for case number 2. I have done slight modification to it, and the changes are that we have replaced L by LC. So in other words, now equations for case number 2 are a kind of simplified. So we have got rid of this complex equations for case number 2. We can use these equations for case number 2. Okay, so temperature distribution for case number 2 equation changes to this, and heat loss by case number 2 equation is now changed to this equation. Remember, these are basically equations for case number 3. The only change is that L is replaced by LC. Now the next topic is fin efficiency. Remember, efficiency is actual case. In this case, it is actual heat transfer rate divided by ideal heat transfer rate. So actual heat transfer rate is that the fin is at different temperatures. For example, you can see the fin is attached to the base surface. The base surface is having temperature 80 degrees C, and the far we move from the base surface, the temperature of the fin drop down. For example, let's say the ambient temperature is 20 degrees C, and ideal case is that we just assume to have an idea that how good the fin is working. Ideal case is that the entire surface of the fin is maintained at base surface temperature. Remember, again, if the ambient temperature in this case is 20 degrees C, so it is obvious, it is clear that heat transfer rate will be more in ideal case, because here throughout the temperature difference is more. In this case, in actual case, as the temperature difference decreases along the length, so heat transfer rate also decreases. So actual heat transfer rate is always less than ideal or maximum heat transfer rate. So maximum or ideal heat transfer rate we can calculate by Newton's law of cooling. This is heat exchange between fin and outside surface. Remember, this is area of the fin, area involved in heat transfer, and in this case this is the fin is exchanging heat with the outside surrounding by its different phases. Remember, Ts is temperature of the base surface and T infinity is temperature of the ambient fluid. And for actual heat transfer rate, we have already discussed the 3 cases. So first we have to identify which case we are dealing with. So we will use the appropriate equation for it. We will pick the equation from the one that we have discussed, the 3 cases, and then we have to divide maximum possible heat transfer rate. Maximum possible heat transfer rate is again ideal heat transfer rate from the fin surface if the entire fin were at base surface temperature. So let's say for the case number 1, efficiency is this is 1 over ml. Remember, you can see from this equation that upon increasing the length of the fin efficiency decreases. Now for case number 3, fin efficiency is, after putting equations, we get tangent hyperbolic ml divided by m into l. This is for case number 3. Now the question is that what will be the fin efficiency for case number 2. So for case number 2, fin efficiency will be we will replace L simply by LC. So this is fin efficiency equation for case number 3. Sorry, this is fin efficiency equation for case number 2. We can also use different figures to find fin efficiency. Remember, on y-axis we have fin efficiency, on x-axis we have epsilon. Epsilon is combination of these, where LC is corrected length, H is convection heat transfer coefficient, K is thermal conductivity, and AP is profile area. Remember, profile area is given in figure for various configuration. So if we have rectangular profile fin, we can find value of epsilon by putting these values. We will get a point on x-axis and selecting our particular curve. For example, we are dealing with rectangular profile, we can have fin efficiency from by using this figure. So if we have parabolic profile or rectangular profile fin, we will use these two curves instead of this curve. Again, this is one other arrangement. If we have a tube, and outside the tube along the circumferential directions we have many fins, so we can find fin efficiency by using this figure. And in this table you can see fin efficiency and surface area of various configuration. So fin efficiency is given and surface area is given for various configuration of extended surfaces. And you can also conclude that fin efficiency for rectangular and parabolic profile is more as compared to rectangular profile, because parabolic profile and rectangular profile uh, utilizes less material. And you can see that the more we go far from the base surface, the temperature of the fin drops down. When the temperature of the fin drops down, it means that heat transfer rate reduces. So if we are in this region which is close to the base surface, the heat exchange is more. If we move away from the base surface, for example in this region the heat exchange reduces, and the temperature, because the temperature difference is less, so we can say that this rectangular and parabolic profile is more efficient than rectangular profile for same temperature conditions. And it is also not justified to use fins if its efficiency is less than 60%. So in practical cases the efficiency normally is more than 90%.